start. Today we have very concrete aim. We want to understand this very important and deep result, counterexample to cancellation problem. And we discussed with Nikhilesh in advance, and he promised me that we can understand it. He will present all explanations, details. Maybe it will be not one talk, but a series of talks. This is okay, because we really want to understand the technique and possible consequences of this result. So Nikhilesh, please.
Yeah, first of all, thank you very much for organizing this talk. Good afternoon to all of you, and good evening to the people from India who have joined. With that, I will share screen. I will try not to be very fast, but unfortunately, I have a very bad habit of moving forward quickly. So please feel free to stop me wherever it is needed. Okay, I hope the screen is visible properly. Maybe I go to full screen. Is it visible?
Yes, thank you.
Okay. So as you can see, the title of the talk is on the family of affine threefolds of a very interesting and special type, given by x to the power my equals to f of x at t. So this is, you can see, view this as an equation in k x y z t over any field. It need not always be a field of characteristic 0, or it need not be always the field of complex numbers. So, and first of all, I should mention this. Even some of the slides and the content of this entire talk is based on the paper by Neena Gupta, which has the same title. It was published in 2014 in Composition. And whenever I use this notation NG, I will refer to that paper. Okay. So what we are looking for. Let K be any field, and I look at the algebra of regular functions of this affine variety. K x y z t mod x to the power my minus f x z t, where for now, let us take m greater than 1. Obviously, some results will be there which will hold even for m equal to 1, but not all of them. So what conditions are we wish that A should have so that this example becomes interesting? So to our problem or our objective is to obtain a criterion for on f x z t for which A will stably be a polynomial ring. What do I mean by stably a polynomial ring? That if I adjoin one indeterminate to this algebra of regular functions A, I will have a polynomial ring in 4 variables. You can see A is of full dimension 3. So if you add one variable, it should have dimension 4, and that we also need to be a polynomial ring over the field K. A, we need to be isomorphic to the polynomial algebra in 3 variables over K. And this hypersurface x to the power of y minus fx at t, this we also wish to see when this becomes a variable in kx, y, z. So for example, suppose by some results or criterion, we have a situation like this, that AW is kxyzt, but A is not isomorphic to kxyz. What we obtain is a counterexample to the Zariski cancellation problem for n equal to 3. So there is another interesting problem. Suppose you have that A is isomorphic to kxyz, but this x to the power my minus fxzt is a variable, or it is not a variable. If it is not a variable, then you get again a counterexample to Abhyankar's Sathe conjecture. I will state those conjectures and open problems. So these conditions are very interesting to investigate. So first, let us fix some notation and definition. These might not be like very familiar to all of you, but I have to follow them for my simplicity. Throughout my talk, K will be a field. I will mention whenever the characteristic I'm assuming to be positive or 0 or K is algebraically closed if needed. For integral domains, everything will be an integral domain, and Noetherian also are contained in B. To denote that B is a polynomial algebra over R, we use this notation B equals to R to the power square bracketed. Or I will say B is Rn, as simple as that. This means B is a polynomial ring in n variables over R. And actually, if I say equal to, I mean it is also whenever they're isomorphic, then also I will use this equality sign. So it stands for both. So first of all, a definition. A polynomial f in KZT is said to be a non-trivial line if, maybe some of you are familiar with the word line. So you can see if KZT mod f is K1, f is said to be a line. But I have used the word non-trivial. What is non-trivial out here? That f is still not a variable in KZT. This is quite strange because in characteristic 0, you will never find an example by a very well-known result of Abhyankar and Moe and Suzuki. But these examples do exist in positive characteristic. That there will be polynomials in KZT. If you go modulo that, it will be K1, but that polynomial will not be a variable. Next is another definition. An R algebra A is said to be an AN fibration over R if A is flat, finitely generated over R, and for each prime ideal of R, the fiber A tensor R over Kp is a polynomial ring of Kp. So what is Kp here? Kp is the field of fractions of A localized at the prime ideal. It's a little bit technical, but best example of AN fibrations are polynomial algebras. You can see for if A is Rn, these conditions will be satisfied. Polynomial algebras are special type of AN fibrations, or we will say they are they're trivial AN fibrations. So it's like being very close to be a polynomial algebra, but it is falling short in some sense. That the condition of being polynomial algebra holds over fibers only. When you tensor with Kp, then only you have it is a polynomial algebra over Kp. And this is another technical definition, but most of you should will know it, that it is a affine algebra is called geometrically factorial. If you tensor it with the algebraical closure of K bar, A tensor K bar is a factorial. Well, probably in my talk today, at least, I won't go into geometric factoriality, but these two definitions of non-trivial line and AN fibration will be needed. Okay. So let's look at the Zariski cancellation. Zariski cancellation problem says that it states a very simple question, that if stably an algebra A, that if I adjoin one variable W to my algebra A, and it is probably a polynomial algebra in n plus 1 variables, was A originally a polynomial algebra in n variables? Obviously, the converse is true. If A is a polynomial algebra in n variables, if you adjoin one variable, it will be a polynomial algebra in n plus 1 variables. But what happens to the answer of this question? Let us look at few simple cases. For example, take n equal to 1. So what the problem translates, that AW is K2, that AW is a polynomial algebra in 2 variables, then is A polynomial algebra in 1 variable? The answer is yes. It follows from a very seminal paper, I will say it's a treasure of a paper, like by Abhyankar, and Heiser of 1972. And let us look at some results obtained in this paper. It's not that they were proving the Zariski cancellation problem. They obtained several results of certain algebra A, some conditions on A, so that it is a polynomial ring in 1 variable. So what we will need this A to be sitting inside some bigger polynomial. So let us look at the results. 3 well-known results. I quote them as AEH 1, 2, and 3 because I will need them later on. So let K be a field. And I stress that it is any field. It does not depend on the characteristic of the field. A be a one-dimensional normal. By normal, I mean it is integrally closed in the field of fractions. A be a one-dimensional normal K subalgebra of Kx1, x2, xn for any n. Then A is K1. So if you find a normal one-dimensional subalgebra sitting inside a polynomial ring, then that affine domain has to be a polynomial ring. Now, a corollary for this result. Let K be a field and A an affine K algebra, and suppose AM is Km plus 1, then A is K1. Actually, this corollary will give you the answer to the ZCP for n equal to 1. You have A1 is K2, it's already given to you. So the condition that AM is isomorphic K over K to Km plus 1 is satisfied. And by this theorem or using this corollary, you will have A equals to 1. A is K1. And over UFD, we have this result that let R be a UFD, D be an R algebra such that R contained in D contained in Rx1, x2, xn, such that transcendence degree D over R is 1. So it's like for the field case, we had dimension 1. That means since A was an affine domain, and so the transcendence degree is same as the Krull dimension. So here is transcendence degree D over R has to be 1, and D is factorially closed in Rx1, x2, xn. Well, one can say D is a UFD also. That is fine. The result will be same. I have mentioned factorially closed for one reason. In the Rx1, x2, xn, then D equals to R1. So it's a little bit generalization of the first theorem over UFDs. Well, why this theorem is interesting, you can see. Suppose some of you are familiar with local and nilpotent derivations. And probably I am taking a UFD and I am looking at a local and nilpotent derivation over Rxy. And we know that the kernel will have transcendence degree 1. And the kernel is factorially closed. So this gives also a proof that the kernel will be of the form some RF. And a remark, oh, sorry. If R is a UFD, then AM is Rm plus 1. Just maybe I put it here. AM is Rm plus 1 will imply A equals to R1. So what the result we had over fields, the same result we can have also over UFDs. Okay. So let's proceed. What happens now? Come to the case n equal to 2. So n equal to 1 is settled. N equal to 1, the answer is yes. The Zariski or cancellation problem, it says that A1 is K2, it will imply that A is K1. For n equal to 2, what will be the statement? It will be that AW is isomorphic to K3, then is A isomorphic to K2. For characteristic 0 case, it was proved by Fujita and Miyanishi Sugi. They were independent. These are two independent papers, and in 1980. And for the result was generalized by Peter Russell in 1981 for perfect fields, and it was further generalized over any field by Bhatwadekar and Neena Gupta in 2015. Now, for n greater or equal to 3, as we will discuss throughout this series of lectures, and it's well known that by this famous result of Neena Gupta of 2014, for positive characteristic, the answer is negative. That there are examples of affine domains. If you adjoin one variable, it will be a polynomial algebra in 4 variables because we have n equal to 3 here. But the original ring will not be a polynomial algebra in 3 variables. And for characteristic 0, well, the question remains open. We don't know what is the case. Now, till now, any questions? Because I can't see the chat. If there is some question in the chat, please let me know. Okay, I'm
excuse me.
Sure.
In the previous page, when you said that is a corollary of AEH.
Yes.
That is AH2.
Yes.
Don't you need that A is normal?
If AM is Km plus 1, see A is a retract of AM. AM is Km plus 1. Km plus 1 is a normal domain. If you have a retract of a normal domain, is always a normal domain.
Okay, so it follows. Okay.
It will follow, but there might be simpler proofs of that. You need not go into the language of retracts also. Okay,
fine.
Well, one thing you are correct. I can't directly say a subalgebra of a normal domain is a normal domain. No, that is false. The subalgebra has to possess something more to make it normal. The easy way, as far as I know it, if you can say it is a retract, then it is normal. Okay.
Okay.
Oh,
Hello.
yes, yes.
Yeah, I just want to clarify one thing in AH3 that D is factorially closed. It is, I think it will be used only to show the UFD property of D, right?
Yes, yes, yes.
Okay. Okay then.
And if, by the way, I should also be very clear, factorially closed. What do I mean by factorially closed? For example, in this case, when I say D is factorially closed in Rx1, X2, Xn, I mean that if I take two elements from Rx1, X2, Xn, probably alpha and beta, I multiply them, the product is in D, then individually both those elements alpha, beta has to be in D. That is the definition.
Yeah, thank you.
Okay. Now, let's look at another problem of a very important problem of fine algebraic geometry. Epimorphism problem for hyperplanes. What does this problem say? Asks, or let's formulate in terms of a question that if I have a polynomial algebra in n variables, I take a single polynomial or go modulo the ideal generated by that, I have a polynomial algebra in n minus 1 variables. Then is this G a variable in kx1, x2, xn? And the Abhyankar-Satie conjecture is the answer to this question 1 is yes. Asserts that the answer to question 1 is yes for characteristic 0, obviously, because you have seen before there are non-trivial lines in positive characteristic. For characteristic 0, n equal to 2 case, this was proved in the affirmative by Abhyankar Mo and Suzuki. So they are both in 1975. Again, these are independent works. There is a work on expansion techniques by Abhyankar and Mo. From that, the Newton-Puiseux expansions, they proved this result for n equal to 2, and Suzuki using geometric techniques. And for n equal to 2, example was given long before. You can see in 1957 by Segre, something called a Segre-Nagata lines. I will also discuss them. So next comes this example of Segre-Nagata. So take a field of characteristic P. S is an integer greater or equal to 2 and such that P is not dividing S. Take this polynomial, the z to the power P squared plus T to the power SP in KZT. What you can see that this is an irreducible polynomial. Well, an argument for that probably will be Eisenstein's criterion, with T being that prime ideal. Anyways, there might be other ways, but this is an irreducible polynomial. And this F, this is a typo. This is, I think this will be capital F. Okay, so this will be a non-trivial line in KZT. KZT mod F will be K1, but KZT is not K1. So this is an example of a non-trivial line. Okay. A corollary.
Nikhilesh, maybe return to the slide just for me to understand. So
yes.
It means in geometric terms that the Abhyankar-Moch theorem in positive characteristic is not true. So
yes,
you have a curve on a plane, and this curve is isomorphic to the affine line, but it cannot be moved to a standard line by automorphism, right?
Exactly. True. So to show, I will try to give a short proof of this result, but for that I will need a corollary from the structure of the automorphism group of KZT, which was given by Jung in 1942 and van der Kolk in 1953. So what is that corollary? This is a corollary which follows from degree arguments, that if there is some f is a variable, it is same as saying that for any set of variables zi, ti of KZT, either the zi degree of f will divide the ti degree of f, or the ti degree of f will divide the zi degree of f. The proof is technical for this result. I will not be able to give it, provide it right now, but it is based on degree arguments. That's it. And also very importantly, because the automorphisms are either triangular or they are like multiplication by invertible matrices only from that. So let us define a K algebra homomorphism phi from KZT to KU. So you can take phi z to be this thing and phi t is this thing. And this phi of z plus z, one can check that. If you want, I will provide you the slides and you can check. Phi of this element is minus u. So phi is onto. This homomorphism is onto. So if I'm able to be, if I am able to detect what is the kernel of phi, I should have an isomorphism. Kernel of phi, this polynomial is in kernel of phi. And since it is an irreducible polynomial, this will be equal to kernel of phi. So kzt mod f will be k1. But now look at the what degree, z degree and the t degrees of this polynomial. This is z degree is p square. This does not divide sp, which is a t degree, and vice versa. And sp also does not divide p square. So by this corollary 2 of the automorphism theorem of kzt, this polynomial cannot be a variable. This is the problem. So let's move now to the case n equal to 3. Well, for characteristic 0, for some special types of G, the answer is yes. If G is the form, these are called as linear planes of the form AXZY. So it is linear in one variable, basically. AXZY minus BXZ. Then the answer is yes. And I also would like to stress that always that condition is satisfied, that KXYZ mod G is K2. It's not that if I pick an arbitrary G of this form, that will be a variable. No, it will never. First of all, we need that KXYZ mod G is K2 and something, a G to be of this some special form. So it was proved this result was proved in 1976 for characteristic 0 and for characteristic other characteristics by Russell in 1976. A generalization of that. Take G to be of this form now, AXZ y to the power n minus BXYZ. Like you can say some A t to the power n minus b of that form. For algebraically closed, proved by David Wright in 1978 and by Amartya Datta and Prosenjit Dash in 2011, the same result for any field K. So these will be variables provided they are planes. And a little bit, maybe not of a special form, but this is result related, somewhere related to proving something is a variable in C3. This is the result by Shulim Kaliman from 2002, that if for almost every lambda in K, the translates of G, that if you go mod G minus lambda, they are planes, then this G is a variable. And this for first proof for complex numbers, and using Lefschetz principle, it was extended to any field of characteristic 0 by Degley and Kaliman in 2009. And for n equal to 4, I would like to give this example because it will be related to Neena Gupta's example in some way. So there are also many other results for n equal to 3 for some special cases. I have not written them all down, some of them only. That a little bit of that form, you take f to be AXYW minus BXYZ, and B is isomorphic to C3. Then f is a variable in the following cases proved by Kaliman, Venerau, and Zeidenberg in 2004. If you can take A to be just from Cx, and this is over complex numbers only. Degree ZB is less or equal to 1. I mean only one of these conditions. If one of these conditions hold, it is a variable. So in these cases, the answer is yes. B is of this form, there is no term containing Z, and the highest degree of Z is 2. And these are a few technical conditions. Height of any irreducible factor, if you take irreducible factor A1 of A, you look at this ideal A1B, intersection CXY, it can have at most 1. So no ideal of height 2 of this form. That's what I mean, or any A is square free. Well, the last two conditions, if you go to the original paper of Kaliman, Venerau, and Zeidenberg, they use some simple affine modifications and some complex algebraic geometry. Well, I'm not very familiar with the techniques, but Neena Gupta and Amartya Datta in a one survey, they have translated those conditions to purely commutative conditions of commutative algebra. These three conditions are as the same as in the paper, and these two can be deduced from the remaining two conditions. Well, why I'm looking at this polynomial. Now, if you see, if I take AXY to be some x to the power m, maybe some w is my y or w, whichever you take, and this is your fxzt of that form. So it will be of the example which we'll want to look at is of this form. So over any field of K of arbitrary characteristic, one has the following special case of the previous result. This is Neena Gupta's theorem from theorem 3.11 from her paper. Let K be any field and A be an integral domain defined by this x to the power my. So I've not written the variable t so that it remains similar. If you set fyz to be plug in x equal to 0 and get a polynomial in yz. So always small f will denote that, and capital F is this whole polynomial. Then the following are equivalent. That if this small f is a variable in kyz, then A is actually a K3. A is a polynomial algebra over Kx. So x is one of the variables. F is a variable in Kxyzw, and F is a variable in Kxyzw along with x. All these conditions are equivalent. Maybe I pause for 2 or 3 seconds so that you can look at the conditions. So main thing is deciding what is fyz. You plug in 0 and check whether it is just a line or it is more than a line, it is a variable and something, and it is over any field. Any questions till now, or I will proceed?
Maybe I will ask some question. Firstly,
Yes.
What does it mean along with x?
Along with x, that you will have a coordinate system. That means x, f, g1 and g2 maybe, such that kxyzw is equal to kx, f, g1, g2.
So it may be included in the system of generators.
Yes, yes. So f
with...
is a part of a coordinate system. That coordinate system will have x.
One more question. These conditions are equivalent.
Yes.
But it's not clear when they are true, right? So this is...
Yes. One needs a proof, obviously.
And I darkly remember that there is such a term, Venero polynomials.
Venero polynomials, yeah. Yes, sir.
This is something like this?
No, they are a little bit different, but some of them are variables, and there is one open case for Venero polynomials, which are yet to be decided.
But these are not these polynomials. This
No,
is
no, not something else.
Okay. Okay, more or less clear.
Okay, sir. I think there's something in the chat. Let me see. Okay, Guy Fulina, yes. Okay, fine. Okay, so let's we will move from this was the first part where you can say the survey of the results. Now we will go into the little bit theoretical things. What is an exponential map? Well, to be very naive, exponential map is just GA action on a commutative ring. So exponential map on a ring A is a ring homomorphism from A to AU. U is an indeterminate over A, which satisfies the following two properties. Well, one can translate those properties to be related to the axioms of the group action. That phi U is the map. So though I say it is a ring homomorphism phi, I will often use this symbol phi U so that I stress which indeterminate I am sending. So there, if I say A to AV, then this map phi will be denoted by phi V or something. And you compose it with the evaluation map at E equals to 0, you should have identity. So A goes to phi U, and so you can see under this phi U, every element alpha goes to alpha plus something. Something times U plus something into U square, and it goes on. And since it is a ring homomorphism, this image of an element of A is a polynomial in A. And the second thing, if you compose, see, phi V, phi U is phi V plus. So what is that? First of all, if I apply phi U, I will go from A to AU. Now, if I want to apply phi V, so a priori we know phi V is only defined from A to AU. How to extend that? So one has to extend phi V from AU to AV, U. Just you keep U fixed, and you apply the usual phi on the elements of. And the composition must be equal to phi of V plus. it looks very technical, but when you deal with a very simple examples, they will turn out to be true. So a remark, phi is also always a algebra homomorphism, and when A is the algebra of regular functions of an affine variety, these exponential maps correspond to the algebraic actions of K plus. And well, a survey is in this book, Essence book, but I will suggest there is a TIFR pamphlet by Mianish, which also gives a very good expositions on these results. So for an exponent, like for, so if we are for characteristic 0, exponential maps will be like local and important derivations, but these are more general things. So for an exponential map phi, we should have a ring of phi invariants. So all those elements of A such that phi A is equal to A, and it is a subalgebra. An exponential map is said to be non-trivial if A phi is not the whole of A. So let's take the first example. This is like a partial derivative, the del by del x, but we are stating this in the language of exponential maps. So take phi on kx and define phi ux to be x plus u. Then the ring of invariants, obviously you can see, is K. This is another example. Phi u on kxy, phi u of x is x, and phi u of y is y plus u plus x u to the power p. Here K is a field of positive characteristic. Here the ring of invariance is Kx, but you can't relate it with a particular local and equivalent derivation in this case. There is a problem. Well, what was the, I will tell you the trick or the back calculation or a naive way to get hold of that local and equivalent. Look at the coefficient of the linear term in U. That will be d of x or something. So here in this case, if I say dx is 1, then obviously you can understand that d is the partial derivative. But here dx is 0 because there is nothing related to u. But dy, the thing is, if I set dy to be 1 here, looking at the coefficient of u, then obviously there is nothing d to the power p of y, that is 0. But here there is some coefficient coming in u to the power p. So exponential maps are a little bit general than local and nilpotent derivations, but they can be related to a particular type of derivations. In general, it is difficult to classify all exponential maps of a ring. So what are these? These are called as locally finite iterative higher derivations. There is a big theory on these things, and well, Mianish's article, as I mentioned on the TIFR lecture notes, there are a very good exposition for that. So I will just briefly note down what are the basic properties. So take a K algebra A, and what is the relation basically? Take phi as an exponential map from A, and define d to the power n of A to be the coefficient of u to the power n in phi A. And you can see individually d to the power 0, d1, d2. I can look at them as linear maps. So define this set D. So it consists of a series of maps. This collection or the family of maps is called as a set of locally finite iterative higher derivations. Now, phi A is contained in A1. So each sequence, if you evaluate at a particular element, these will have finitely many non-zero elements. Because after a certain power of u, there is no more terms. These are K-linear maps. They satisfy this Leibniz rule. D0 is the identity map. This comes because we have taken phi to be an exponential map. So phi of A starts is A plus something. So D0 is identity. And this is called as the iterative property. Di dj is I plus j cj d of I plus j. This comes from criteria 2. When characteristic K is 0, D1 is a local and nilpotent derivation. And this phi can be written as exponential of u d1. And you know what is exponential summation over I, 1 by I factorial. So you can see every dn can be written in terms of d1 when characteristic K is 0. But since there is a 1 by I factorial, you can guess when the characteristic is positive, we will have problems. So this is the distinction between characteristic 0 case, where you can write every dn in terms of d1, but in characteristic positive, it is not always possible. But obviously, still there will be locally finite iterative higher derivations. This is, so if with every exponential map, there is a LF IHD, and every LF IHD corresponds to an exponential.
Let me try to understand in
Sure.
my terms. So
Yes.
when you have a characteristic 0, then any action of the additive group is given by exponent of locally nilpotent derivations.
Yes.
So this is the series with denominator, which there are some factorials in these denominators, and this doesn't work in positive characteristics.
Yes.
So this language of exponential maps, as you defined, or this higher iterative higher derivations, this is some substitute, which is equivalent in 0 characteristic, but
Yes.
also work in positive characteristics.
Yes.
And what you say that here higher derivations are not defined by the first one, right? So we have specified.
Yes, that is the distinct. That is the difference. That d2 I cannot write 1 by 2 factorial d1 square. Not always in positive characteristic. See, the problem will be only with the power p in those cases. What is d to the power p? D to the power p square, d to the power p cube. Those things.
But modulo this, we have such a language to describe J actions. Because, say, we know that there is a theorem that invariance of one-dimensional unipotent group, this, they are always finitely generated. And it's under some conditions, say, linear representation of additive group. And as far as I remember, in positive characteristics, this is an open problem. But maybe this is because this is a difficult language and it's not easy to prove some finite generation and so on. Okay, this is just my personal reflection. I'm sorry. Okay.
So some properties of exponential maps. Well, again, I will give these are few references. I want to specify if you want to take a quick look what properties can be used for exponential maps. Though they were originally probably appear in Miyanishi's lecture notes, but they were written nicely in the articles by Makallimov and Krashiolov of 2005, and there's another article of Krashiolov of the same year, and also the paper of Neena Gupta. So let A be an affine K domain and phi belongs to EXPA, be a non-trivial exponential map. So what we should expect? So you can compare these properties with the properties of a local and nilpotent derivation, and you will see a lot of them turn out to be same. A phi is factorially closed in A, like we have the kernel of a local and nilpotent derivation is factorially closed. Factorially closed implies algebraically closed, so A phi is algebraically closed in A. Transcendence degree of over K of A phi is 1 minus the transcendence degree. This condition 4 is like a local slice condition, that there exists an element in the ring of invariance that if you invert it, it becomes a polynomial algebra after localization. A1 by C is A phi 1 by C1. Transcendence degree A over K is 1 implies that A is a polynomial algebra over the algebraic closure of K. And A phi will be K bar because A phi has to be algebraically closed. And again, for any multiplicatively closed set of A phi, you can invert that and get another exponential map, which is non-trivial S inverse phi, and the ring of invariance will be S inverse A phi. One who is familiar with local and nilpotent derivations will immediately realize that all these properties are true for them. So exponential maps look a lot similar to local and nilpotent derivations in these terms. Well, now there will be a curiosity. Does every result of LNDs are true for exponential maps? Well, I do not know. That can be a very good project for one to investigate what properties of locally nilpotent derivations are true for exponential maps. But I can't, right now, me and one of my colleagues was looking for an answer to one case but we do not know whether it's true or not. I can share it with you. That we have a result for LNDs over Rxy, where R is a Noetherian domain, maybe a UFD to be, or a HCF ring. If I take a fixed point free local and nilpotent derivation, what do I mean by fixed point free? That the ideal generated by dx and dy is 1. then that LND has a slice. Is it true? The answer for local and nilpotent derivations is yes. That has been proved by Bhattacharya and Datta, and later generalized by SN and Morbach probably. But I do not know for exponential maps whether that will be true, or at all how will I translate the condition of a fixed point free LND in terms of an exponential. So there are results which probably one can investigate and look whether they are true or not. But a priori, both the things look a lot similar. And why I've chalked down these results, because for the proofs of the upcoming lemmas or theorems, we will need these properties. Okay. Now, like we have the Macaulay-Limonov invariant and the Dirksen invariant for.
Sorry, and again, let me interrupt you. Let us go to this lemma. I don't understand property 5. Maybe here on the right-hand side, you consider A as an algebra over algebraic closure, because how can you prove that A contains algebraic closure?
Algebraic closure of K in A.
This is, yes, yeah, I see. Take
so it may not be the whole of that. The ones who are elements of A which are algebraic over.
I see. Then clear.
Okay, thank you. Okay. Now, the Dirksen invariant of a polynomial. Dirksen invariant will be the algebra over K generated by all non-trivial exponential, by the ring of invariants of the all non-trivial exponential maps. Like when we say in terms of LNDs, we say the algebra generated by all the kernels of non-zero local and nilpotent derivations. So one very easy lemma, which you can obviously guess, that what will be the Dirksen invariant of a polynomial algebra? It has to be the whole thing. Why? You take the partial derivatives basically, but let us state it in the language of exponential maps. So I define phi I. My A is kx1 x2 xn. I define phi I from A to AU to be a K algebra homomorphism defined by phi I of xj going to xj for I not equal to j, and phi I of xi is xi plus. So it actually corresponds to del del xi. So what is A phi will be all the variables apart from xi, because everyone is fixed by phi. Hence the Dirksen invariant. So this becomes a tool which will be used to distinguish an affine domain from a polynomial algebra. So if you have an affine K algebra such that it has positive transcendence degree over K, and the Dirksen invariant is not the whole ring, then A cannot be a polynomial ring. Well, the converse need not be true. There might be polynomial algebras where the Dirksen invariant is the whole ring, but there might be affine algebras for which the Dirksen invariant is the whole ring, but it is not a polynomial. That is a different question altogether. But in this direction, we can say if the Dirksen invariant is not the whole ring, then A can never be a polynomial. So this is the main theorem of Gupta of 2014. So A is kxyzt, and as you remember, the polynomial is of this form, x to the power my minus fxzt, where m is greater than 1. G is x to the power my minus fxzt. I will denote this polynomial as capital G. Fzt, small fzt is f0zt. Then the following are equivalent. A is isomorphic to K3. A is isomorphic to Kx2. Fzt is a variable in Kzt. Kxyzt is Kg3. Kxyzt is Kxg2, is saying that it is a variable along with x, that thing. A is stably a polynomial algebra, and the Dirksen invariant is the whole ring. A is an A2 fibrillation over Kx, and Dirksen invariant is the whole ring. Kzt mod f is K1, and dk is A. And dk is A. The first K group of A is K star, and A over K is geometrically factorial. Well, for now, I am avoiding K theory in these lectures, but if needed, if we have time, I can go into that too. Remember, in positive characteristic, we have non-trivial lines. So what happens if f is a very non-trivial line, like kzt mod f will is k1, but fzt is not a variable. So obviously you need that dka is not the whole ring, so otherwise this theorem will be false. So this second last condition is violated through the Dodson invariant condition, and as an equivalence this condition is valid. So that case will be the counterexample case for the Zariski cancellation. But a priori this is not related to ZCP right now. It is just a theorem on certain type of affine threefolds. Now, if you can remember or just take a note of this result, let's look at some consequences. Okay. So K is a field of any characteristic, and this is we have what we have. So A is a polynomial ring in 3 variables over K, if and only if f0zt is that is small fzt is a variable in kzt. This provides a general framework for understanding the non-triviality of Russell-Chorus threefolds. If you remember, the Russell-Chorus threefold of the first kind is given by this equation x square y plus x plus z square plus tq. This is of the form of G. You take m to be 2 and f x zt to be x plus z square plus tq. Now look at what is f of 0 zt, that is z square plus t, that is singular. So it can never be a line, forget a variable. So Russell-Chorus threefold will not be isomorphic to K3. So this gives another proof. And also a family of similar polynomials. If A is isomorphic to K3, we know that G is a variable along with X. That means KXYZT is KXG2. This provides a partial case of the Abhyankar-Sate conjecture. What was Abhyankar-Sate conjecture? We would have said that KXYZT mod G, which is A, is isomorphic to K3. Then is G a variable? That was the question asked by Abhyankar and Sate. Well, what we have shown that if it is isomorphic, A is isomorphic to K3, then this G will always be a variable. And not only that, a variable along with X. And there is another theorem by Sate and Russell that on linear planes, with this extends this result to for the case n equal to 4. So for not only for the Zariski cancellation problem, even for the epimorphism problem or the Abhyankar-Sate conjecture, these examples are interesting to look at. This is another A is isomorphic to K3, if and only if A is equal to KX2. And this is another problem regarding A2 fibrillation. So there is a result by Sate that A2 fibrations over a DVR or discrete valuation rings are trivial. Well, but that theorem requires an hypothesis that the field that DVR should have the field of rational numbers contained. That means characteristic 0. So there are examples of non-trivial A2 fibrations over positive character, over a field of positive characteristic, over Kx, where Kx is a K is a field of positive characteristic. And this shows that A is a non-trivial A2 fibration if and only if F0zt is a non-trivial line. Because if it is a variable, then this is a polynomial ring and then it is a trivial A2 fibration. There's nothing non-trivial about it. So, and this is another theorem. Theorem may be okay. So A is of the same form, m is greater than 1. If F0zt is a line, then K1 is K4. See, I am not specifying whether it is a non-trivial line or a variable. So whatever it is, in any characteristic, this A1 is always isomorphic to K4. And I think this result is written m greater than 1. The exact theorem is true even for m equal to 1, but not the previous results. Recall that if F0zt is a non-trivial line, then by the previous theorem, we know that A can't be isomorphic to K3. So this will give you a counterexample to the Zariski cancellation problem. And actually, you will see it's a family of counterexamples. you take F0ZT to be any non-trivial line in KZT and create this affine variety. This will stably be a polynomial algebra in 4 variables always, but it will never be isomorphic to the polynomial algebra in 3 variables. If K is a field of positive characteristic for each M, one can create such a family, like for putting x square y, x cube y like that, and take just FZT, that where FZT is any non-trivial line. Then this has been also be proved by Neena Gupta that AMF and ANG will be isomorphic if and only if M and N and F and G are equivalent. That means there is an automorphism of FZT which takes F to G. Thus, over any field of positive characteristic, there is an infinite family of non-isomorphic rings which are stably isomorphic to K3. Anyways. Okay. Any questions till now? One can ask, because now after this, I will start with the proofs.
So just to summarize, up to some moment, all results were conditional. It means that if we have at least some conditions, then they are equivalent to this, and that. And
well, sir, if you have, we have the equation of this form, x to the power my minus fxzt. I am saying the f0zt is something if and only if the condition is not one direction, it's like equivalent. If you look at the theorem, see, till this is a statement. So there is no condition yet here before I start my equivalence. Only you can say M has to be greater than 1.
Just a moment. So this is a statement of the following form. These conditions are equivalent.
Yes.
We don't know whether they are true or not, but at least they are equivalent to each other.
Yes.
And in order to apply this, we have to start from something non-trivial, and the non-trivial point was at the beginning of your talk, that in positive characteristics, there is such a polynomial f in the third condition, which is non-trivial line. Yes?
Exactly.
And based on this, we put this into this equivalent condition, and we obtain what? That A is not isomorphic to affine through space, right?
Yes, if you take a non-trivial line.
But at the same time, when you add one variable, you obtain affine force.
Yes, affine force space over any field, and obviously positive characteristic. And non-trivial lines will be only in positive characteristic, but this theorem that A1 is K4, where did I, okay, just 1 second. That this thing is K4, this is over any characteristic. Only you need that this to be a line. And since non-trivial lines are lines, a priori lines, so there is no problem.
And both results are difficult to prove that this is.
Yes, sir. I will say it's quite difficult,
Okay, in any case, you are going to explain us at least some scheme of the proof so that we can estimate how difficult it is.
Yes. Of course, I will do. At least they were for some me. But this is why I would have loved a board talk, but what we can do with the situation, we can't tell. So, see, I will start with the proofs now. So you let me know when I can stop, and we can continue in the next lecture, because I want to go slowly so that there is no hurry in something. Okay. So lemma 1. Let's start with lemma 1. So let's, well, you will ask me why I'm stating this lemma, how it is related. Well, up to few lemmas, it will not be, it is like a chain of events going on, but where it is climaxing or where it is culminating to, that will be clear a little bit later. I am sorry for that inconvenience. Let K be a field, A be an integral domain defined by Kx, Y, Z, T mod this, where M is greater or equal to 1. Now, Fzt is that usual thing. Suppose X is the image of capital X in A. Then the following are equivalent. A is factor A.
I'm sorry, one more interruption, because proofs are usually difficult. So maybe you have some scheme. What are you going to prove? In which order for us to follow?
Actually, I will prove of a, I will not say difficult, but what we can do here is we will prove not every statement. I will prove a modified version of this. Maybe one condition removed from here, that they are, I will prove that they are equivalent. But for that, to show that they are equivalent, I will need some results that I will establish.
So our aim now is to prove this theorem about
This theorem,
the space, not about space.
Yes, and sir, if I get time, for now the slides which I prepared till now, I have skipped the proof of this, that this is A1 is K4. But if I have time, I will give a proof of this also.
Okay, I see.
So two main things, theorem A and theorem B, that we have to prove. And we have to build up to prepare for this. Okay. So let K be a field. A is an integral domain defined by this. This is easy. This lemma is not difficult. The following are equivalent. This is just commutative algebra, that A is UFD. This element X is a prime in A or a unit in A. And FZT is irreducible in KZT or FZT is in K star. Okay. So let's look at one implies two. So what I have to show? I have to show that if it is a UFD, then either X is prime or X is a unit. So enough to show that it is either an irreducible element because it is a UFD. So concept of irreducible elements and prime elements coincide. So I can, it's enough to show that X is a irreducible element or X is a unit. So let Z and T denote respectively the images of capital Z and T in A, and suppose X is not irreducible. But X is also sitting inside K X Z T. You can see X, Z, and T are algebraically independent. So this ring is actually isomorphic to K3, polynomial algebra in 3 variables, which is a UFD. And X is irreducible there. So if it is not irreducible in a subalgebra, it means there exist 2 elements A and B in A, such that X is AB, but not both of them belong to A set. Just using the definition of an irreducible element. So suppose the first element A does not belong to KXZT. Now take A to be sitting inside A1 by X. This you can write KX1 by XZT. As a result, A will be of the form of some alpha by X to the power I, and B will be of the form beta by X to the power J for some alpha beta. Then what you have? X to the power I plus J plus 1 equal to alpha beta, because X equals to AB. So A is this, B is this. So X to the power I plus J plus 1 equal to alpha beta is in KZ. Now, X is prime in KZ. And X to the, what I have obtained? Alpha beta is a power of X, power of a prime. So individually alpha and beta have to be powers of X in KX. So alpha is some lambda X to the power R and beta is some lambda inverse X to the power X, satisfying R plus S to be I plus J plus 1. Thus, now if you can plug in, you will see A is lambda this X to the power R minus I, and B will be, sorry, there is a typo here. It will be, B will be equal to lambda X to the power S minus J. But what we assume that A does not belong to KXZT. So this R minus I can't be positive. So R minus I is less than 0. And this means actually X inverse is. Anyways, this is technical, or you can easy. 2 implies 1. So let's look at the statement. 2 implies 1 is X is either a prime or a unit. Now I have to show that it is a UFD. Well, we will use the Nagata criteria that if a Noetherian domain after inverting a prime element is a UFD, then the original Noetherian domain is a UFD. X is a prime element is given to us. A1 by X is KX1 by X2. This is a UFD. So by Nagata's criteria, it is a UFD. Yeah, and if it is a unit, well, A1 by X is X. And 2 and 3 are obvious because if you go A mod xa, k, this is x goes away, it is kyzt mod f, which is kzt over f1, a polynomial algebra of kzt over. Well, you can say why I am doing this lemma. This lemma involves certain important things which are needed later also. If not, if the lemma is not needed in every result, but what I have to look at, what is A1 by x? A1 by x is a polynomial algebra of kx1 by x, where A is given by this equation. What is A mod xa? So two things I will take from here. That what is A1 by x, what's the structure of A1 by x, and what is A mod x. A mod xa is kyzt mod. Now this becomes small f. So kzt mod f1. Now if your f is a line, kzt mod f is a k1. So A mod xa becomes k2 if f is a line. This is what lemma 2 says. Now these conditions again are equivalent. That A mod xa is k2, that means what I said right now, that fz is a line. A is a A2 fibration over kx. This is I will need, because one of the conditions of my theorem involves A2 fibration. So 1 implies 2 follows from the definition of A2 fibration. Well, let's look at the definition of A2 fibration. Recall the definition of A2 fibration. Finitely generated, flat, and everything, that is fine. Main thing was, if you tensor with a prime ideal P over of R, A tensor P should be KPN. So take that prime ideal P, if A is given to be your A2 fibration, take prime ideal P to be the ideal generated by X. Then what we have? We have A tensor over KX with KP. And what is KP? KP is the field of fractions of R mod P or KX localized at which is K, basically. KP is K. So we will have A mod XA after tensoring, and that will be K2, KP2. It's just that if you write it down and do a little bit of more like commutative algebra, 1 line or 2 lines, you will arrive at this. So being an A2 fibration implies this. 2 implies 3. A mod xa we already know from the previous lemma that it looks like kzt mod f is k1. Now I will use a corollary of AEH. If you remember, corollary of this says what? A mod xa is already k2. So say this is my capital B. Kzt mod f is my capital B. What I have obtained is B1 is k2. Then by the AEH corollary or the cancellation for n equal to 1, I will have B is k1. 3 implies 1. Fzt is a line. So what is A mod? This always holds. A mod xa, kzt mod f1. So well, if kzt f is a line, kzt mod f is k1. So A mod xa is k2. Well, now I have to show for every prime ideal the fibers are preserved correctly. So let P be a prime ideal of Kx other than Xkx, because for this A tensor Kp is isomorphic to A mod Xa, which is K2. Now if X does not belong to P, then this prime ideal can be looked as a non-trivial prime ideal in Pkx 1 by x. Since A1 by x is K1 by x2, what we have, A tensor Kp will be Kp2. Because if you, after tensoring with Kx 1 by x, it has already become a polynomial algebra. So if you tensor with Kp now, it will be Kp2. Thus A will be an A2 fibration over Kx. Okay. These were 2 small technical lemmas. Now again another thing, coming to filtrations, which will appear in the subsequent results. A proper Z filtration of an affine domain A over a field K is a collection. Well, Z filtration everybody knows probably. So first 3 conditions are for Z filtrations, and proper I mean that actually that GR will be a domain. Associated graded ring, I need to be a domain. So if you take something from AN but not in AN minus 1, something from AM not in AM minus 1, the product will be contained, can never be contained in AN plus M minus 1, basically. It will be in n plus m minus this. A proper Z filtration is called admissible if there exists a finite generating set gamma of A such that for any n in Z and f in An, this f can be written as a finite sum of monomials in elements of gamma such that each of these monomials is an element of A. So finite sum of monomials of some special homogeneous elements, and these homogeneous elements coming from A, basically. So not every proper Z filtration will be admissible, but in our cases, we will have the filtrations which we will define will not only be proper, will be admissible, because we are dealing with finitely generated K algebras. So getting hold of a finite generating set should not be difficult. Only thing we have to be sure what filtration we are giving so that our generators are homogeneous. So the filtration in the example induced by a graded structure of a finitely generated K algebra is admissible. Now, like homogeneous local and nilpotent derivations, you have something called as homogeneous exponential. Now, let A be a graded ring. Then it uses a usual graded structure to the polynomial ring AU with U as a homogeneous element. We have an exponential map phi initially from A to AU. Now A is graded. If I say A to be, if I want my exponential map to be called homogeneous, what I need extra? That this ring homomorphism is a graded ring homomorphism. And immediately you will see that if phi is homogeneous, then A phi now will be a homogeneous subring of A, if phi is a homogeneous exponential. So let's give one example. You take kxy and phi 1 to be exponential map. Phi 1x is x, that means the partial derivative with respect to y. This is homogeneous. It sends homogeneous elements to homogeneous elements. And a phi 1 is kx. However, if I take this exponential map, a to au, phi 2x is x plus 2yu minus u square, and phi 2y is y minus. This will not be homogeneous because phi 2x, x doesn't go to a homogeneous element. So there are exponential maps which are not homogeneous. One has to be careful when we look at which examples we are taking. Now, similarly, we will create the associated graded ring now. But now we will keep in mind our filtration is proper and what extra thing comes into when it is admissible. Any proper Z filtration will define a Z graded integral domain because it is proper. GRAS summation AI mod AI minus 1, and the usual thing, the row going A to GRA defined by rho A is A plus AN minus 1. Now, some remarks. One has to be careful while working. This rho is not a ring homomorphism in some sense, because if there is a scenario like that, if for some index I less than n, you have A1, A2, AL, which are elements of AN, but not in AN minus 1. But summation AI goes into something much lower. It belongs to AI, and I is strictly less than. Then what should be rho of summation JAJ? By definition, since summation JAJ belongs to AI minus 1, rho of summation JAJ should go to summation JAJ plus AI minus 1, that question. And it is not 0. But individually, if you do rho AJs, each AJ is contained in AI, and AI AN minus 1 has to contain AI because I is strictly less than. So summation rho of AJ is 0, but rho of summation AJ is not. So additive property is not preserved. But suppose A has proper Z filtration and there is a finite generating set gamma which makes it admissible, then GRA is generated by rho gamma. Since if A1, A2, AL and these belongs to AN minus 1, rho of summation JAJ will be this, and this multiplicative property will be whole. So for admissible proper Z filtration, GRA will be generated by the image of this set gamma. And this is another important feature. Suppose if there is a Z graded algebra structure, A is already a graded ring. And then there exists a proper Z filtration defined like this. You do not take the component to be Ci, but you take up to n, like a degree at most n, sort of that thing. Ans to be direct sum of I less or equals to NCI. Moreover, now you will see GR of A, sum A is same as A. But here, under this isomorphism, what does A go? A goes to the maximum homogeneous component of maximum degree. This will be used. And this is a famous theorem of Dux and Hadas and Makallimana from 2001, which will be needed in our proofs. And I won't be able to give a proof of this theorem. It is a little much more away from what we are doing. Let A be an affine domain over a field with an admissible proper Z filtration, and GRA be the induced Z-created domain. Let phi be a non-trivial exponential map on E. Then phi induces a non-trivial homogeneous exponential map phi bar on GRA such that rho of A phi, that the image of the ring of invariance, is contained in the GR of A phi, GRA phi. So ring of invariance of phi bar is GRA phi bar, and rho of A phi will be contained. We have similar results for LNDs also in the same of the same flavor, but this holds even for exponential maps. Okay. This is answered. Any questions till now? Then, because next is another aspect. Okay.
I just try to understand geometrically what is a passage from an algebra to its graded variant. Maybe this is some degeneration of a variety, right? And
Maybe so.
Here you explain that if we have a GA action on some variety, then this action also
on GR.
Yes. On the graded algebra.
Yes.
Mm-hmm. Nikhilesh, maybe when you will find a logical point to stop today and continue next.
I think this is a nice place, because after that, I won't want to break the continuity, because there's no point in doing a part of a theorem, stopping and doing the next part the next day.
I see.
Because after that, okay, I will state maybe one or two results I will state, because that I am not proving right now, but you can also enjoy those results because I won't proving that. But after this lemma 3, here we will use all these filtrations. Before that, I will stop. Okay, let's mention these results. And so Russell-Sate criteria, well, I have to explain what is Russell-Sate criteria means. It's just like we want to find some conditions on a subalgebra so that it is a polynomial ring in one variable over something. So sort of that. So these two theorems are reformulations of results of Russell and Sate from 1979 by Neena Gupta and respectively Bhattacharya and Datta. And there is another theorem which Neena Gupta generalized to higher dimensions, which is needed again. So what are these results? These are actually, I will say alone, they are quite nice results. One can use it in other areas also. Let K be a field, F is in KXY such that if you tensor over KF, with K round bracket F, KF1, then F is a variable. You can see this condition means F is a line, because if you take a tensor over, so what is not I'm saying, if you say, if I invert F, this means KF contains 1 by F. So what it says is KXY 1 by some polynomial in F is KF 1 by some polynomial in F1. So something like this was proved by Kaliman for KXYZ, if I am not wrong. Anyways, so this is one theorem we will use. Another theorem is, if there are two integral domains such that D is a finitely generated R algebra, suppose there is a prime element pi in R such that pi remain prime in D. So pi is an element in R. I lift pi from R to D. I want pi to remain prime there, so it should not break it up into some other factors. If I invert pi, D is a polynomial algebra over R in one way. Pi D intersection R is pi R. This means there is the map from R mod pi R to D mod pi D is injective, and R mod pi R is algebraically closed. If you have all these conditions, then again D is R. So these are techniques to prove something is a polynomial algebra over a subalgebra. And compare, if you compare with theorem RS1, this theorem is RF for 3 variables. K is a field, F is in KZT, such that KF is algebraically closed in KZT. Suppose KZT, now you tensor over KYF. Instead of KF, you have KYF. This is KYF1 for an indeterminate Y over KZT, then KZT is K. I will share the slides so that also you can have a look at the results. And I think with this, today I will stop so that from the next class I will start.
Okay, thank you very much for your very nice, clear, and well-structured talk.
I am sorry because we have less time. These results will be interesting once we use them. I'm just stating certain theorems, certain lemmas. So how they come into the picture, and why these results, some are very landmark results, and the Abhyankar Sate results, or I have not stated any proof of that because it's not possible for me. Even those papers are seminal papers. We are using them as if they are very trivial results, but they are not at all trivial.
I see. Are there any questions, comments, suggestions for the next time?
Maybe a little bit slower.
Maybe I have a suggestion, because
Yes.
Today you gave us a nice overview, general picture, and it's clear that this is connected with many things, that it will be difficult for us to understand all of this. So maybe next time, to minimize our task, we have 2 statements. This algebra is isomorphic to the algebra of polynomials in 4 variables, and this algebra is not isomorphic to the algebra of polynomials in 3 variables. So let us concentrate on the proof of these 2 facts. And also there are 2 ways of proving. Firstly, you can formulate some lemmas. Lemma 1 proof, lemma 2 proof, lemma 3 proof. And then you say, as you remember, in lemma 1 and lemma 2, we have this and that. And from this result, we obtain. And this is quite difficult to follow.
Yes, sir.
So maybe I will propose another way. We have the formulation of the result and put main steps, the scheme of the proof. We will prove this, and this give us the result. And then go to details.
Okay.
And then we can follow the proof.
Yes, sir. I will definitely make certain changes.
Okay. So, any more comments? If not, then thank you very much. In fact, your talk was very motivating because I was listening, and for me, there is a very easy, how to say, gradation. What is a good talk and bad talk? For me, good talk is a talk when I listen to this, I think, so nice that I'm a mathematician. How I invest time in this, and this is such a pleasant profession and so on. So during your talk, I was proud that I'm a mathematician, and it was, I don't know, some
Thank you, sir.
motivation for me to do something else. So this was a good talk.